Welcome to this deep dive brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today, we are undertaking a really critical deep dive into radioactivity. It's the fascinating heart of Unit 13, nuclei. Our mission is simple, really. We want to unpack these concepts, the nucleus, binding energy, and why things decay so clearly that you'll just get it. Okay, so let's just jump right in. We all know atoms are mostly empty space, right?
Right?
But the nucleus, it holds almost all the mass in this unbelievably tiny volume. But have you ever really stopped to wonder why? I mean, why doesn't the nucleus act with all these positive protons just fly apart?
That is genuinely mind-boggling. Coulomb's law says they should repel each other violently. So if the nucleus is that small, like a pinhead in a stadium, what force could possibly be strong enough to overcome that massive repulsion?
Excellent question. And this is where things get really, really interesting. Just think about a normal household smoke detector. You can buy one anywhere. Inside it, there's a tiny, tiny speck of something called americium-241. And right now, as we speak, that americium is actively undergoing radioactive decay. It's constantly emitting these invisible alpha particles.
So that's how it works. We have radioactive decay happening in our homes for safety.
Exactly. We literally rely on the constant breakdown of unstable nuclei. And that decay proves two things. One, that the nucleus can be unstable, and two, that there must be an incredibly powerful force holding it together in the first place. So the core idea, basically, is that the nucleus is this extremely tiny, dense ball of protons and neutrons. We call them nucleons collectively. And this whole paradox, this repulsion versus density, it's resolved by a completely new force.
The strong nuclear force.
The strong nuclear force. Okay.
Let's use an analogy. Imagine the nucleus is like a really crowded room.
The protons are people inside who are pushing away from each other. That's the Coulomb repulsion. They hate being so close. But there's also this mysterious, super strong friendship force that only works when they're shoulder to shoulder. It's so powerful it makes them stick together.
So we call it the strong nuclear force because it just completely overpowers that electromagnetic repulsion.
Absolutely. At those tiny distances, we're talking femtometers, it's about 100 times stronger than the electrical repulsion. Now, for exams, there are two properties you absolutely must remember. One, it's extremely short range.
So if the particles move apart even a little bit, the force just vanishes.
It drops to zero, exactly. And two, it's charge independent.
Meaning the force between a proton and another proton is the same as between a neutron and a neutron.
Yes, or a proton and a neutron. The force doesn't care about charge. But here's a challenge for you. If this force is so short range, how does it hold together a massive nucleus like uranium-238?
That's a good question, because if the force only works between immediate neighbors, then a proton on one side of a giant nucleus, it shouldn't feel the pull from the other side. But the Coulomb repulsion, that travels across the whole nucleus, right? Pushing everything apart.
That's spot on. And that leads to a concept called saturation. In a large nucleus, each nucleon only interacts with its direct neighbors. That's the saturation property. But the Coulomb force, it doesn't saturate. So the total repulsive force grows much faster than the total attractive nuclear force as the nucleus gets bigger.
And that's why really heavy nuclei become unstable.
Precisely.
Yeah.
That is the fundamental reason radioactivity exists. To really get the scale, just try to visualize this. Imagine the nucleus is a sphere of tightly packed marbles, all vibrating. If we can magnify that tiny sphere to the size of a tennis ball,
Okay.
the nearest electron would be orbiting 10 kilometers away.
Wow. 10 kilometers.
That scale shock, that extreme density, it just shows you why you need such an extremely strong force. Okay, now let's get into the technical details, how we actually quantify this strength, which is what will get you marks in the exam. We characterize a nucleus by Z, its atomic number, which is the proton count, and the neutron number, and A, the mass number, which is just Z plus N. Let's see how insert formally defines the key concept we use to measure all this, which is mass defect. Could you read that for us?
Yes. The insert definition states, the difference in mass of a nucleus and its constituents, delta M, is called the mass defect and is given by delta M equals ZMP plus A minus ZMM minus M. This energy required, EB, is related to the mass defect by EB equals delta MC squared.
Right. That formula can look a little scary, but let's just break it down into simple steps. Step 1. We take the mass of all the individual protons and neutrons when they are separate, and we add them up. Step 2. We use a mass spectrometer to measure the actual mass of the nucleus after they've all combined. And here's the crucial part, step 3. You'll find that the measured mass of the nucleus is always less than the sum of its parts.
Always less.
Always. That difference, that delta M, is the mass defect. It's literally missing mass.
Hmm.
So, step 4, where did that mass go? It was converted 100% into energy. We call that the binding energy. And we calculate it using Einstein's famous equation, EB equals delta mc squared. This energy is the superglue holding the nucleus together. Now, to compare the stability of different nuclei, I mean, a heavy nucleus is obviously harder to break apart than a light one, so we don't use total binding energy. We use a more useful value, binding energy per nucleon, or EBN.
So that's the total binding energy divided by the number of nucleons.
Exactly. It tells us the average energy needed to pull just one nucleon out. The higher this value, the more tightly bound the nucleus is, and therefore the more stable it is. Let's take a quick conceptual example, helium-4. It has 2 protons and 2 neutrons. The sum of the masses of these 4 loose particles is about 4.03188 atomic mass units, or U. But when they combine to form the helium nucleus, its measured mass is only 4.00260 U.
So the mass defect, the difference, is 0.02928 U.
Right.
But that's such a tiny amount of mass. Does that really create a lot of energy?
It creates an enormous amount. The conversion factor is key here. 1 U of mass is equivalent to 931.5 MeV of energy.
Mega electron volts.
Right. So our tiny 0.02928 U mass defect converts to roughly 27.3 MeV of total binding energy. That's huge on an atomic scale. And since helium-4 has 4 nucleons, the binding energy per nucleon is 27.3 divided by 4, which is about 6.8 MeV per nucleon.
And that's a high number.
Very high, which confirms why helium-4 is so incredibly stable. It's often emitted whole as an alpha particle during decay. And, understanding this binding energy per nucleon curve is the key to understanding all nuclear energy. The curve actually peaks around iron-56. Anything lighter, like hydrogen, can release energy by combining to get closer to iron. That's fusion.
And anything heavier, like uranium, can release energy by splitting apart, fission.
Exactly. Both processes move towards that peak of stability at iron-56. Now let's connect this stability idea directly to radioactivity. Since the EBN value starts dropping after iron-56, large nuclei are basically unstable. They're energy-rich, so they need to find a way to become more stable. They do this by reducing their size or adjusting their neutron-to-proton ratio.
So radioactivity is just the process of an unstable nucleus trying to become more stable.
That's all it is. It's a spontaneous process where an unstable nucleus transforms by emitting particles of radiation.
And this involves the 3 decay modes, right? Alpha, beta, and gamma.
Yes. Let's touch on those briefly. Alpha decay is common in very heavy nuclei like uranium. The nucleus just throws out an alpha particle.
Which is basically a helium nucleus, 2 protons, 2 neutrons.
Exactly. So the parent nucleus loses 4 from its mass number and 2 from its atomic number. It's a quick way to shed some weight.
And beta decay, that one's a bit more confusing.
It is because something transforms inside the nucleus. In the most common type, negative beta decay, a neutron turns into a proton. To do this, it emits an electron, which is the beta particle, and something called an antineutrino.
So the total number of nucleons stays the same, but the atomic number goes up by 1 because of the new proton.
Precisely. This happens when a nucleus has too many neutrons. It's trying to get a better balance. And this is actually governed by another force, the weak nuclear force. And finally, there's gamma decay. This usually happens after an alpha or beta decay. The nucleus is often left in an excited high-energy state.
Like an electron in a higher orbit.
A very good analogy. And when the nucleus drops back to its ground state, it releases that extra energy as a high-energy photon, a gamma ray.
And gamma rays don't change the number of protons or neutrons.
Nope. They change neither A nor Z. They're just pure, highly penetrating energy. But the crucial thing about all these decays is that they're completely random.
You can't predict when any single atom will decay.
Never. We can only talk about the probability of it decaying over a period of time. And this brings us to the concept of half-life. The half-life is just the time it takes for half of the radioactive nuclei in a sample to decay. And it's an intrinsic property. It doesn't depend on temperature, pressure, anything.
So if I have 100 grams of an isotope with 1 hour half-life, after 1 hour, I'll have 50 grams left.
You're right.
Then after a second hour, 25 grams, and so on. It's an exponential decay.
That is exactly right. The decay is predictable on a large scale, even if individual atoms are random. And that's what allows for things like carbon dating in nuclear medicine. Okay, now for the really important part for your exams. The mistakes that trip up almost everyone. The silent killers.
Okay, I'm ready.
Misconception number 1. A lot of students think that binding energy is some kind of repulsive force that makes things decay.
I can see how that might happen.
It's completely wrong. Binding energy is the glue strength. It's the energy you must add to pull the nucleus apart. High binding energy means a strong, stable nucleus.
Right. So binding energy quantifies the attraction, not repulsion. It's the energy required for separation. I need to remember that.
Please do. Misconception number 2. People think mass is destroyed in a nuclear reaction.
But we just said mass is lost, the mass defect.
It's not destroyed. It is converted to energy via E=mc². Mass isn't conserved by itself, but mass energy is always conserved. That missing mass is now the binding energy.
Okay, so it's a conversion, not destruction. Got it.
Finally, misconception 3. The idea that you can speed up or slow down radioactive decay with heat or pressure?
You can't.
Absolutely not. The half-life is a nuclear property. It's determined by the forces inside the nucleus, and it is completely independent of any external physical or chemical conditions. All right, let's lock this all in with some memory anchors. Remember this one phrase: mass lost equals energy gained. Binding energy is the glue. The stronger the glue, the harder to break.
Mass lost, energy gained. Stronger glue, harder to break. Okay.
And for a physical anchor, try this. Hold your hands close together, almost touching. That's your nucleus. Now press them together, really hard. The resistance you feel when someone tries to pull them apart, that resistance is the binding energy. You have to add energy to separate them.
I like that. It's a good way to visualize it.
And one final extreme association. The density of nuclear matter is about 2.3 times 10 to the power of 17 kilograms per cubic meter.
That's a number I can't even imagine.
It means that 1 cubic centimeter of it, the size of a sugar cube, would weigh 100 million tons.
100 million tons.
Yeah, as much as Mount Everest, crushed into a sugar cube. That's the kind of density that demands the extreme strength of the nuclear force. Okay, let's summarize the 3 most important exam-safe points from today. 1. The nucleus is held together by the ultra-short-range, charge-independent, strong nuclear force. Its stability is measured by the binding energy per nucleon. 2. Mass defect is the missing mass when nucleons combine. This mass isn't lost. It's converted into binding energy, which is the energy needed to take the nucleus apart again. And 3. Radioactivity is a spontaneous process where unstable, heavy nuclei decay to become more stable. The rate is defined by the half-life, which is a constant and is not affected by external conditions. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is ProfSam, right?
Yes, ProfSam.com.
Oh.
Thank you for diving deep into the world of nuclei with us today, and we wish you the very best in your studies.